Hello everyone, welcome to this new session on electromagnetic fields. Today we will discuss about the del operator. Del operator is very important concept in this subject. So today we will discuss all about the del operator. It is a vector operator, but we cannot directly consider it as a vector unless it comes with a vector. So it is called as spatial differential vector operator, where spatial indicates something which is related to space. So this operator is represented by this symbol, and this is used to represent space in 3 dimensions. So our vectors are working in space, either it is electric field or magnetic field, they are working in space, and this del operator is used to represent them. So it is a spatial vector operator which operates in space. So in general form, we have 3 coordinate system which we use here in this subject. Normally we use 3 coordinate system. First one is Cartesian coordinate system. Second one is rectangular coordinate system, and third one is spherical coordinate system. So if our object is operating in a 3D space which is in Cartesian coordinate system or rectangular coordinate system, then del operator is given by this function. So this del operator is first, it gives 3 directional partial term, dou by dou x, dou by dou y, and dou by dou z, and along with that there will be 3 directions. So 3 directions for dou by dou x, direction is ax cap. For dou by dou y, direction is ay cap. For dou by dou z, direction is az cap. So this equation is very important. This is given in Cartesian. Same way we have to see the equations for cylindrical as well as spherical. So second one, here we can see there is a cylindrical coordinate system. In this coordinate system, a cylinder is considered, and if we want to study its behavior in space, so the entire equation here, RHS, you can see it representing the equation in cylindrical coordinate system. This entire term we can represent by a single operator del. So it will give us simplicity to write the equation. So big equation we can convert into a single operator. So in this operator, what we have? First we have r term, dou by dou r, then we have dou by dou z, then we have dou by dou phi. So along with dou by dou phi, we get 1 upon rho or r term. That is because unlike in the cube or Cartesian coordinate system where all the sides are straight, but in cylindrical there is a curve. Due to this curve path, we get this additional 1 upon rho term. So this is the expression for del in cylindrical coordinate system. Now let us see the next one. Here we have a system for spherical coordinate system. Spherical coordinate system, what are the 3 coordinates? Rho, phi, and theta. So we have dou by dou r or dou by dou rho, then dou by dou theta, dou by dou phi. So this is direction for rho. Then as this is a spherical coordinate system, we have 2 curves, one as cylinder, one for spherical. So for these 2 curves we get this additional 1 upon r sin theta and 1 upon r. So this is the del operator for spherical coordinate system. Now del operator we can use with different scalars or vectors, and their product will decide whether it is divergence, curl or gradient. So if we want to discuss about gradient, gradient is a product of del operator with a gradient is nothing but the product of del operator with any scalar quantity. So for example, we can consider say del dot voltage. Voltage is a scalar quantity. So this one is called as gradient of voltage. Now second one is divergence. Divergence is dot product of del operator with any other vector. For example, del dot d bar, where d bar is flux density, it is nothing but a vector. So this is called as divergence of d. Now curl, if we take cross product of del operator with any vector, then it is termed as curl. Suppose del cross E, where E bar is electric field intensity. So this one can be termed as curl of electric field intensity. So these are three common forms of del operator we use in this subject: gradient, divergence and cross product. By using these two, we also have divergence theorem and Stokes theorems, that also we will discuss. Then gradient of a scalar. So let us explore it. Let us consider our quantity is scalar, say voltage V. Then del dot V is termed as the gradient of voltage. Now following equation gives the gradient values of scalar like we have seen for the voltage. Gradient of a scalar is a vector, that is, when we multiply del with a scalar, then it becomes a vector quantity. We have to remember it if some objective type question we have to face. Now if we recap, first one equation is for Cartesian. Cartesian is very simple to remember: dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap. So now if we write V here, if V is any quantity, so here we have to write del dot V. So this term in 3 dimensions should be multiplied here. Then next one is for cylinder and third one is for spherical. In cylindrical coordinate system, so here also we have to multiply it with V. If right side if we are doing V, here we have to write del dot V, here also del dot V, but this time it will be a vector, and here del dot V if right side we are using voltage. So these are 3 forms. Then it has some properties, gradient properties, where W, say W and V are 2 scalar functions. Then it follows following rules. Say first one, del into W plus V will be equal to, now this del will be multiplied with this one, and again this del will be multiplied with this one, so we will get del W plus del V. Similarly, if there is a product of W V, so we can have say V delta W plus W delta V. If there is division of gradient quantities, so it will become V delta W plus W delta V by V square. And similarly, if we are taking some power v to the power something, then it will be n v to the power n minus 1 delta v. These are the properties of gradient. In the subject, voltage is a gradient we normally use. The next one is divergence of a vector field. Divergence means what we do, we take the dot product of any vector along with del. So this is del dot d. How we will represent del dot d in full form? So del dot d in Cartesian coordinate system, we can represent it as, say, del dot d is equal to first term dou by dou x ax cap. So here we will get d. So this may be dx plus dou by dou y dy into ay cap plus dou by dou z by dou z into az cap. So here we can observe that this d can be represented as dx, then its direction, plus dy, its direction, plus dz, its direction in 3 dimensions. So all the quantities are represented in 3 dimensions by using del operator. So in 2 dimensional, suppose divergence is very easy to understand. Like we can consider an example of some balloon. Divergence means what? It is a outward force going out in all the directions. Suppose we will take an example where there is a balloon and that balloon is filled with water. Suppose you take one balloon, it is filled with water. So if you take some small needle and puncture it, what will happen? It will blast. Water flow will go out in all the directions. So this is outflow. So either we may have outflow or inflow of the force lines that represents the divergence. So del dot any vector represents the force lines either going out from a point or getting collected at any point, at given point. Now curl is a rotating force, circulation. So when we take cross product, we call it as a curl. Del cross any vector is a curl, rotating curl, like a twister. This is example of a curl. Divergence is outflow or inflow, and curl is the rotational force. So the divergence So what we have to remember, at any given point, the divergence of vector is just a single number that represents how much flow is expanding at that point. So the divergence is a scalar, that is, divergence of vector gives a scalar output. We have to remember. In short, del dot f bar any vector is equal to divergence of f. It is outflow of force where area going towards the 0, area shrinking to 0, and force is going out in all the directions. So what we have for curl, it is the cross product. Del cross any vector is a curl. Del dot any vector is divergence, and del dot with any scalar is gradient. So we have to remember curl, divergence and gradient. So how we write curl? Suppose curl of electric field intensity, it is given by del cross E bar. This is curl of electric field intensity. Del cross H bar is curl of magnetic field intensity. We represent it like this. So divergence is all about outflow of fluids. Example is balloon. If we explode, force goes outside. Curl is all about rotation of fluid. Let's imagine that a vector field F representing fluid flow as shown in the figure, and the fluid is circulating. So this is rotatable in 2D as well as 3D as shown in figure. This is example of rotating curl. So these curl expressions we can write in different forms. Suppose we have one force, say del dot F. So how we write del? Del is dou by dou x, dou by dou y. This should be dou by. So this should be dou by dou y, and this should be dou by dou z. So F force may be in x direction, F1, F2 in Fy direction, F3 in Fz direction. Similarly, del cross F, cross product, we use the matrix form to solve the cross product. So after using cross product, we get the simplified equation like this for del cross F, where del operator is combination of three directional components. So let us check the proof for these two. So say del dot F. Del is equal to dou by dou x, Ax cap, plus dou by dou y, Ay cap, plus dou by dou z, Az cap. That is our del. And force is F1 Ax cap plus F2 Ay cap plus F3 Az cap. Now if we take dot product, so what happens for the unit directions? Ax cap, similar direction, they become 1. Ay and Ay, they become 1. Similarly Az, they become 1. So in del dot F we get dou F1 by dou x plus dou F2 by dou y plus dou F3 by dou z, and the direction component will not be visible in that equation. Then let us check for next one, del cross F. Suppose del cross F, we get this. So let us explore it. Cross product is calculated by the matrix form. Suppose del cross F, we read it as curl F. So three directions, Ax, Ay, Az. Then three direction partial terms, dou by dou x, dou by dou y, dou by dou z. Then the force F1, F2, F3. Now let us take the cross product. So once we take it, we get this expression for curl. So this is expression for del cross F. So in short, del cross F is curl F, that is circulation per area. So there are two theorems related to these two. One is Stokes theorem, another one is divergence theorem. So Stokes theorem, in short we will see. Stokes theorem is used to convert line integral to surface integral. So many times it happens that we have to deal with the conversion of the integrals. So suppose this is line integral f dot dl bar. So if we have to convert it to surface, what we will do, we will take the curl. So we will get simply curl f dot ds. That means del cross f dot ds bar. And divergence theorem is used to convert surface integral to the volume. So we will see these two theorems we frequently use in the subject, and this theorem is derived from the Green's theorem. Green's theorem is similar to Stokes theorem. The only difference is that Stokes theorem is studied in 3D and Green's theorem is. Now say this is example f dot dl bar, this is line integral. To convert it into surface, simply we have to take cross product with del. This is nothing but Stokes theorem. Similarly, there will be divergence theorem. So here we have divergence theorem. So divergence theorem is for converting say volume to surface. So del dot f, if it is volume, then we can simply write it as f dot ds. So or f dot ds can be converted into the volume. So surface and volume conversion can be used by divergence theorem. So these are about the del operators. In next session we will see all about electric field intensity and other topics. Thank you. Have a good day.